All right, so we want to talk about sample spaces and events. So the idea is as follows. An experiment is an event that has an observable outcome. So rolling a die is an example of an event. The experiment has 6 possible results, which is the die can show a 1, a 2, a 3, a 4, a 5, or a 6. The numbers 1 through 6 are the possible outcomes of the experiment, and the set of all possible outcomes is called the sample space. So an experiment is just any event that's observable, and we want to talk about the sample space, which is the set of all possible outcomes for whatever that experiment is. So let's take a look at our first example. So, example 1, determine the sample space for each experiment. A red die is rolled and the number is observed. Well, that's going to be the same as what we just had above. So our sample space S is going to be the set of numbers 1, 2, 3, 4, 5, and 6. So B, a red die and a white die is rolled. The numbers are observed. So what are our possibilities in our sample space? Well, if we have both a red and a white die, each die has the possibility of rolling a 1 through a 6, right? So to help us visualize this as maybe a table, if we have each of our rolls, it would be possible then to have a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And finally, our last row would be 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So our set of all possible outcomes, S, would be this. So if we roll both a red and a white die, we would have these as a possibility, right? And I chose to list the red die first for no reason whatsoever. If you did the white one first, it's not going to change your sample space. Okay, let's take a look at our next couple. So this time, let's talk about C and D a little bit. So C says 2 red dice are rolled and the numbers are observed. So how is that going to be different from our previous one? Well, the implicit assumption here is that if we're rolling 2 identical dice, that's going to make them indistinguishable, right? So what would be our possible outcomes? Well, it would be like what we had above, but if we couldn't tell the dice apart, a 2 and a 1 and a 1 and a 2 would look like the same thing, right? So in this case, our sample space would be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 1, 1 would be indistinguishable. 1, 2 would be indistinguishable. So the next thing we would need, so 3, 1 would be indistinguishable from 1, 3. So we wouldn't need anything essentially in the rest of this column because we wouldn't be able to tell it apart. So then the next row would be 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. But then 2, 2 through 2, 6 would match all of these ones that were in this row before, right? And so we don't need any of those again. So then our next row would start at 3, 3, 3, 4, 3, 5, 3, 6. Similarly, we would have 4, 4, 4, 5, 4, 6, 5, 5, 5, 6, and 6, 6, right? So that would be our possible configurations, right? Because the reason we're not including anything that's down here below the diagonal, if I had, say, 3, 2, if I can't tell the dice apart, rolling a 3 and a 2 is the same as rolling a 2 and a 3, because the events are indistinguishable. All right. Lastly, 2 red dice are rolled, and the sum of the numbers are observed. Okay, so this time, we're rolling the dice, but then we're adding them up. So what would be our possibilities? Well, let's go back to this one. If we roll 2 dice, what's the smallest possible number we can get? 1 and a 1, and what's that sum? 2. And if we roll 2 dice, what's the biggest number going to be? 6, 6, which would give us 12. And can we roll every number in between? Certainly. So our set would be the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So that would be the sample space for that experiment. So notice, depending upon what outcome we are observing, rolling 2 dice can have very different sample spaces, right? It depends on what we're doing. So the experiment depends on what we are trying to observe. So rolling a couple of dice can be interpreted a few different ways depending on what we're observing. So, for instance, in B and C, having a red die and a white die changed the outcome. In D, if I had a red die and a white die, would it change my sample space? Does it matter that I can distinguish the dice when I'm adding the outcomes together? No, because it's still going to give us the same sums, right? So we have to be a little bit careful. So there's a lot of language baked into these problems. So we have to be very careful that we're reading carefully and understanding what it is precisely we are being asked. Because rolling 2 dice can mean a lot of different things depending on which observation or what the experiment entails. All right. So here's one for you guys. So you try. 2 cards are drawn out of a standard 52 card deck. So hearts, clubs, spades, and diamonds, ace through king, right? So what would if we're choosing 2 cards out of a standard 52 card deck, what would our sample space look like? Trying to list all of them is going to get really, really long, so you might want to just describe it in words. I mean, you can, but if you had to choose 2 cards out of a standard 52 card deck, 2 cards are observed, what's our sample space going to look like? All right, so first off, we're probably not going to want to try to enumerate all of these, right? Because how many possible outcomes are there? Well, this is a two-stage experiment. In stage 1, how many choices do I have? 52. And in stage 2, after I've taken out one card, how many choices do I have? 51. 52 times 51 is a pretty darn big number, right? So if we were to multiply 52 and 51 together, what do we get? 2,652. Do you want to try to write out all those combinations? No. But it would look something like you would pair each card with every other card, right? So there would be a lot of them. So there are a lot of outcomes to this event. All right. Example 2. All right, so a survey was conducted that asked 8th grade students if they played a musical instrument, they played a team sport, and their GPA range. And their possible choices were below 2.0, 2.0 to 3.3, and above 3.3. So we want to determine the sample space of this event. So once again, this is a multi-stage thing. Let's draw a tree diagram to help us out. So we have our student, and the first question they were asked is, do they play a musical instrument, right? So this is, they play a musical instrument. And this is they don't play. Then, what was the next thing? Do you play a sport? Or no? So, team sport. And no team sport. Then down here, we also have the same two choices, right? And no team sport. And then finally, what was the last thing? We have GPA, and we're going to have 3 choices, right? So we're going to have above 3.3, 2.0 to 3.3, and then below 2.0. But then what's going to happen? We're going to have the same thing for all of these, right? Because that's our stage 3. So then what would be all of our possible outcomes? Well, we would have to go to the end of each of these. So first of all, how many outcomes are there going to be? Well, if we get to the very end, there's going to be 1, 2, 3. For the next one, 4, 5, 6. For the next one, 7, 8, 9. And for the last one, 10, 11, and 12, right? Because we repeat each of these. So the first one is going to be play instrument. If we go all the way to the top, they play a team sport. And their GPA is going to be above 3.3. Then the next one's going to be the same 2 things, but it's going to be 2.0 to 3.3. And then the last one in the top branch is going to be the same two things again, but it's going to be below 2.0. Then, what would our next branch be? Plays an instrument, but no team sport, right? So our next group would be play an instrument again, no team sport, and then we would have above 3.3, plays an instrument, no team sport, so these first two are going to be the same again. And this is going to be 2.0 to 3.3. The next one in that group, first two don't change again, and then below 2.0. All right, so we've exhausted this upper branch where we play an instrument. Now we're going to come down. So our next group is they don't play an instrument. Then we have a team sport. And then above 3.3. First two don't change. And then 2.0 to 3.3. And then below 2.0. And then lastly, we don't play and no team sport. No team sport. And then above a 3.3. First two don't change. 2.0 to 3.3. And below 2.0. So in this case, it was still a little tedious, but we could list all 12 possible outcomes. We used a tree diagram to help us diagram what was happening, right? So our first possibility was they played an instrument or they didn't. The next possibility was they played a team sport or they didn't. And then the last possibility was they either had a GPA above 3.3, a GPA between 2.0 and 3.3, or a GPA below 2.0. That gave us 2 times 2 times 3 possible outcomes, which is 12, which was exactly all of them that were listed here. So those are all the possible outcomes in the sample space, right? Were that any of these things. So those were the 12 outcomes that they could be. So for instance, if we looked at this one, it would be they don't play an instrument, they do play a team sport, and their GPA was between 2.0 and 3.3. So in practice, we will be interested in a certain part of the sample space. So in all the previous examples, we were listing all possible outcomes in the sample space. So from the previous example, we may be interested in students that play an instrument that didn't play a sport and had a GPA in the range 2.0 to 3.3, right? This set of students is a subset of the sample space. Given a sample space S and an event E is a subset of the sample space, the outcomes in E are called favorable outcomes. We say that E occurs in a particular experiment if the outcome of that experiment is one of the elements of E. In other words, if the outcome is favorable. So when we have a sample space, we're often going to be interested in events that aren't the whole sample space. So like we said, for instance, the students who play an instrument, didn't play a sport, and had a GPA between 2.0 and 3.3 would be a subspace of that space or an event. We could even make it broader. What about all the students that play an instrument? That's a subset, right? We could ask questions about that subset of the entire space. So an event E, if we're doing an experiment, if that's what we want, we call that event favorable. We'll do some examples to illustrate what we mean. All right, so let's take a look at our first couple of examples in example 3. A red and white die is rolled, and the numbers facing up are observed. Describe the following events as subsets of the sample space. The sum of the numbers is 13. If you roll 2 dice, can you get a sum of 13? No. So our event E in this case is going to be the empty set, right? Because it's not possible. You can't add 2 dice and get the sum of 13. It's just not possible. Okay, so B, the sum of the numbers is 7. So first of all, how many ways can you roll 2 dice and get the number 7? Well, if we go back and look at our diagram that we made up here, if we're trying to find numbers that sum to 7, 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 6 and 1, right? So how many different ways can that happen? Well, all of those on the diagonal, so that's going to be 6, right? So our possibilities are going to be, not with a blue highlighter, 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1 and 6, right? And all of those give us 7. So our event E would be any of those combinations of the red and white dice, right? So if our ordered pairs are of the form red and white, we're saying the first one is the red one and the white one is the second one, right? So it would appear that each of those would happen, we would have it happen in 6 possible ways. So that would be our subspace, or the event, as a subset of the sample space. Okay, let's look at our next ones. Okay, so C is the white die is less than 3. So first observation, in this, does it care what the red die is? No, the only thing we care about is the white die, right? So if we come back up here and look at our chart, so the red die is our first one in this chart, and the white die is the second one. And what do we want the white die to be? Less than 3. So the white die is less than 3 here, and it's less than 3 here, right? So it's going to be those events, and we don't care what the red die is. The red die could be any number from 1 to 6. So the events in our sample space would be those first 2 columns in this table, right? So our events would be, if our white die is less than 3, we're going to have 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1, and 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, and 6, 2. We can't add any more because if we move to 3, 3 is not less than 3 for the second coordinate. So this would be our set for this. So how many possible outcomes are there in that set? 12, right? Okay. So D, it says the number on the white die is less than the number on the red die. So for this one, I'm going to actually bring down this whole chart to make it a little bit easier to illustrate what we're trying to show. So our ordered pairs, remember, are of the form we arbitrarily chose the red die to be first. And what did we want? We want the white die to be less than the number on the red die. So that means that the second digit has to be smaller than the first digit, right? So here, 1, 1, they're equal, so that doesn't work. 1 is less than 2, so that works. So all of these work. Not true, not true. Okay, 2 is less than 3, so all of these are going to work. Not true, not true, not true here. 3 is finally less than 4. 4 doesn't work. 4 is less than 5, and 4 is less than 6. And 5 is less than 6, right? So the ones that we highlighted in orange show us when the white is less than the red. So how many events would there be in that space? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So E is the orange above. I mean, we could list them all out, but that's the idea of what's going on. So that would be our event that the white die is less than the red die. And that's how that could occur. All right. So now we want to talk about, well, how do complements, unions, and intersections work with what we've just been talking about? So basically, if we think back to when we were talking about our set theory, we have unions were or statements, and intersections were and statements. Complements were all of the things that were not in a set. So the complement of an event E is the set of outcomes not in E. Thus, the complement of E represents the event that, missing a T there, the event that E does not occur. The union of the events E and F is the set of all outcomes in E or in F or in both. In symbols, E union F represents the event that E occurs or F occurs or both. The intersection of the events E and F is the set of all outcomes common to E and F. Thus, E intersect F, or E and F, is the event that both the event E and the event F occur. All right, so let's look at some examples of our ands and ors. Let's do this a little So example 4, a red and a white die is rolled and the numbers facing up are observed. Describe the following events as subsets of the sample space. So the red die and the white die have different numbers facing up. And then follow up, what is the complement of that event? All right, so I'm going to use this picture quite a bit. So what's the event that we're trying to do? We want the event that the red and white die have different numbers facing up. Well, let's start with the second question first. What would be the complement of the event? So if our event is the white die and the red die have different numbers facing up, what's the complement of that? What's that not happening? Well, that would be them having the same numbers facing up. So the complement of the event would be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So then the event having different numbers facing up is going to be everything else. So remember, an event and its complement never have any points in common, and the two of them together will always cover the entire space. So having different numbers facing up means that the die don't have the same number. So then the complement of that event would be they do, which is the diagonal of that diagram. So how many events are there where they have different numbers facing up? 5 plus 5 plus 5 plus 5 plus 5 plus 5 is 30. Then the number of events in the complement is going to be 1, 2, 3, 4, 5, 6, right? So E is the blue, and E complement is going to be the red. All right, let's continue with these. So let's visualize our next one. The white die is greater than 3, or the red die is less than 4. So let's let E be the event. White is greater than 3. And let's let F be the event. Red is less than 4, right? Let's use our diagram again because it will be helpful. So here we have an OR statement, right? So remember, an OR statement is a union. So the event that we want, which I'm going to call A, is going to be E union F, because that is our OR statement. So with an OR statement, I want this or this. So let's highlight that the white die is less than 3. Well, that's these two columns, right? We did that earlier. And F is the event that the red die is less than 4. Well, that's going to be these two. And since it's an or, we get something that looks like this, because we want the event E or the event F. Okay, so then our event E or F would be represented by this. So how many things are in the event E union F? 6, 12, 15, 18, 21, 24. Six, 12, 15, 18, 21, 24. Right? All of the stuff in yellow is in the event E union F. So how many things are not in E union F? 12. Good. All right. Let's keep going. So our next example is very, very similar to the one we just did. In fact, what is the only difference between B and C? I read that wrong. White is greater than 3. Yeah, we need to go back. Apparently, I can't read, which is a problem. Because what was my event E? Let's back up. The white die is bigger than 3. So the white die is the second one, right? So if the white die is bigger than 3, that would have been here, here, and here. I was thinking of this previous example up here where we did the die was less than 2. Yeah, so remember our ordered pairs were R and W. So if white is bigger than 3, that's 4, 5, or 6. So that's here. And if red is less than 4, so red has to be less than 4, it's going to be here. Okay. So that would be our event. Well, they're not going to be. So this time, we want to do something very similar. The white die is greater than 3, and the red die is less than 4. The only difference between this is we have an OR up here, and here we have an AND. So let's define our events in the same way. So E is going to be the set where white is greater than 3. So the white has to be greater than 3 is going to be these again. But this time we have an AND. So let's make our set F going to be the red die is less than 4. And so red is less than 4 is going to be this. So we get the same idea happening, but we'll notice something a little bit different happens this time. So this time we want an AND, which means it needs to be in both sets. So the AND is actually what is in green. So in this case, E and F would be those sets. So 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, and 2, 6 to be explicit, and 3, 4, 3, 5, and 3, 6. So or means it's in either set, and means it has to be in both. So when you mix yellow and blue make green, right? And that's why we got this set in green representing the and, because that's both that are yellow and blue. Or in other words, the ones where the white die is greater than 3, but the red die is less than 4. And in that set, there would be a total of 9 events. Let's take a look at D. The white die is not greater than 3, and the red die is not less than 4. So we've got this not in each of these, and that's really describing the complement. So if we let E be the event that white is greater than 3, then E complement is white not greater . And similar, if we have F is red is less than 4, then F complement is red is not less than 4.
But when it be with white, isn't it just what the white?
So those would be our events, and the event that we want is white is not greater than 3 and the red die is not less than 4. So what we really want is, we have an and, we want E complement intersect F complement. So E complement can be rephrased well, we'll do that part later. Let's grab our diagram and then we'll do our rephrasing in a second. So let's take our E complement is white is not greater than 3. Well, if white is not greater than 3, that would mean white would have to be what? Well, if you're not greater than 3, or equal to 3, then that would mean you were what?
Less.
So white greater than 3 would be everything over here. So not greater than 3 would be everything over. And similarly, if we have our F, if red is not less than 4, well, that's the complement of if red is less than 4, that would be this part, but we want not less than 4. So that's going to be this part. So we want the and of this, which is going to be this part down here, right? Is going to be our stuffing green because it's an and. So we could rephrase each of these things and we'll see that we get the same thing. So if you rephrase not less than or not greater than 3, so if white is not greater than 3 is the same as white is less than or equal to 3, right? And F prime is red not less than 4 is white greater than or equal to 4. Which, if we do the same thing in our highlighting, we get the same picture, right? All right. If E and F are events and E intersect F is not the empty sets, the sets are said to be, and E intersect F is the empty set, the sets are said to be disjoint or mutually exclusive. The events do not have any outcomes in common, and therefore it is impossible for them to occur simultaneously. So when two events have an empty intersection, or their and is equal to the empty set, it means it's impossible for them to happen at the same time. The name for that is we call them mutually exclusive events. So we want to look at our sample here and determine if the events are mutually exclusive. So a die is rolled. E is the number is greater than 3, and F is the number is odd. We want to know, are those two events mutually exclusive? Well, let's enumerate the things in E. So if the number is greater than 3, that means the number could be 4, 5, or 6. And F is that the number is odd. Well, that means it could be 1, 5, 1, 3, or 5. So we check their intersection. Well, what is E intersect F? Do E and F share any elements in common? 5. So the intersection of E and F is the number 5. Because 5 is both greater than 3 and an odd number. So this is not equal to the empty set. So are our events mutually exclusive? No. Because to be mutually exclusive, E intersect F has to be empty. So not mutually exclusive. A die is rolled. E is the event that the number is even, and F is the event that the number is odd. No. So if E is the event that a number is even, our possible outcomes are 2, 4, and 6. If F is the event that the number is odd, its choices are 1, 3, and 5. So then if we check E intersect F, do E and F have any events in common? No. So our intersection is empty. So then by definition, they are mutually exclusive. Because the event E intersect F is empty. All right, let's take a look at our next example. C, 2 dice are rolled. E is that the sum is greater than 7. F is that the number facing up on either die is not 1. Okay. I'm going to grab our chart again to help out with this, to help us visualize what the events are. So we have our chart, and our event E is that the sum is greater than 7. So to get 7, that would be this diagonal, right? But we don't want 7. What do we want? Greater than 7. So those events aren't in the sample space. So to get numbers bigger than 7, okay, 2 plus 6 is 8. 5 plus 3 is 8, 4 plus 4 is 8, 3 plus 5 is 8, and 2 plus 6 is 8. So then everything over here, if I add any of these numbers, I will get a number bigger than 7. The ones on the diagonal, I got exactly 7, which I didn't want, and anything above the diagonal would be less than 7, right? So that's my event E. What's my event F? The number on the number facing up is not 1 on either die. So there we go. So not 1 on either die would be this event in blue. So then here, E intersect F would be the stuff in green. So then these ones, that's not the empty set. So this one would be not mutually exclusive.